Hello everyone. In this video I want to talk about ionization energy as part of the periodic trends series of chapter 7. Okay, so ionization energy, as I mentioned here, as you can see on the screen, is the energy required, the energy added, the energy needed, the endothermic energy is needed to remove an electron, to break a bond. Remember, anytime you break bonds, that's endothermic, that's energy added. Okay. Now notice the definition goes on to remove an electron from an isolated gaseous atom or ion. So notice I have the sodium atom. Okay, it's in the gaseous state. So in other words, it's completely removed from its neighbors. Okay, it's the single lone sodium atom, and I've removed an electron, giving us a plus charge, a positive 1 charge. Okay. All right. Now on the periodic table, we see that the trends increases up a group and increases to the right. So the highest ionization energies, the most energy it takes to remove electrons, is the upper right. The least amount of energy is the bottom left. Okay. So if we take a look at a periodic table, and I go here, and I draw a periodic table real quick. There we go. Down here has the low ionization energies. And here I have high ionization energies. So what does that mean for us? What that means is that down here, these, all in this range here, lose electrons very easily because it doesn't require much energy to take them away. Okay? How do we know that? What evidence of there is that? Large atoms tend to have large distances between the positive attractive nucleus and the negative electrons. Okay? These would be the atoms down here. Okay. Not only that, but their configurations also end in S1, S2. Okay. Sometimes S1, S2, S2, D1, that kind of thing as well. Okay. So these electrons down here love to lose electrons because it doesn't require much energy to strip them away. However, these atoms up here, these elements up here, really don't want to lose electrons at all, so they have high ionization energies. In other words, it takes a lot of energy to strip away those electrons. Okay, so these tend to retain or keep their electrons. Okay, and then instead they like to do something else. They like to gain them. Okay, so down here these like to lose, and these like to gain. Okay. These like to lose electrons, these like to gain electrons, okay? So if they would rather gain up here, then they keep their electrons they already have, okay? Now, if we take a look at the table of first ionization energies, okay? First ionization energies, you'll notice as I move from left to right on a periodic table, they indeed go up, okay? Those numbers go up. Now, when we have something called multiple ionization energies, we're looking for patterns now. To remove one electron is not too bad. Let's take a look at magnesium, okay? If I look at magnesium, it's Mg, and I look at the electron configuration, it's 1s2, 2s2p6, I think it's 3s2. Yeah, 3s2, okay? So we know that magnesium likes to form Mg plus 2 ions on normal natural cases. Well, is there an explanation for that? Yes. If we take a look at the first ionization energy, it's 738 units of energy, or kilojoules per mole, to remove an electron, added. If we take a look at the second ionization energy, it doubles. It always, by the way, multiple ionization energies, it always takes more energy to remove successive electrons. Okay? So in other words, 738 for the first one, it goes up. It always goes up. Okay? But now you'll notice I enter a threshold here. It jumps from 1451 up to 7,733. There's a definite jump here. It's non-linear, okay? This tends to be setting up some type of linear trend, but now the 7,733 is non-linear. In other words, when I see a huge spike in energy, we see that the atom has indeed lost enough electrons to probably have something very comfortable, probably a noble gas notation, or a full S&P sublevel, a full octet, in other words. So if we take a look up here, this is loss of 1 electron, Mg plus 1. Loss of all 2 electrons, Mg plus 2. There's the full octet. Life is good for magnesium, for the magnesium ion. Okay? So what are we looking for? We're looking for linear and then a huge jump. Not bad, huge jump. Okay? That's what we're looking for. Okay, so you might see test questions that has, say, for element X, it'll be like 5, 10, 15. I'm just making up numbers here. 5 units of energy to lose the first electron, 10 electrons to lose the second, 15 electrons to lose the third one, and then 150. So that would form a +3 ion naturally. Okay, it doesn't want to lose the fourth ion. So those are multiple ionization energies. Okay, we'll go through some of these in class. Again, more of this in class. Notice this is the ionization energy trend, okay? So down here, very low, moving up to very high in the top right-hand corner, okay? So this is ionization energy. Actually, it's just first ionization energy. Okay, now let's move to the second topic, which is the opposite, called electron affinity. And electron affinity, if you can have an affinity for something, it means you're getting it. So this is the energy released. So energy released, the energy lost, the exothermic energy when an electron is added. Remember, anytime bonds are broken, you have to add energy to do that. But this one says the energy released. So anytime bonds are made, energy is released, and that's exothermic. Okay? So these will be negative in nature. These energies will be negative in nature. Okay, the greater the negative number, the greater the chance of gaining an electron. So the period trends, as you can read here, it increases from left to right and increases up. Okay? Now we'll talk about this exception in class. You can read it here. Turns out that fluorine is much smaller atom than chlorine. Actually, it lends to more electron-electron repulsion. I'll talk about that in class. Okay? But if we take a look at a periodic table, what do we see here? We see low electron affinities, high electron affinities. Okay, now it increases to the right and up. These, as we mentioned before, have high affinities. They don't want to lose electrons, they'd rather gain. They want to gain electrons. So they have high affinities. They release a lot of energy, in other words, to gain those electrons. These down here, these metals, love to lose electrons. So they have low electron. I'm sorry, I already wrote that. Let me write it this way. I had my mind on something else. So they'd rather, with the low electron affinities, they would rather lose electrons. So they have very low affinities. Okay, so they don't want to gain. So they don't want to gain. They would rather lose. These don't want to lose up here. They would rather gain. Notice these are nonmetals, and these are all metals down here. Okay? So the trend, as you just saw, here's another example. Notice we are just considering main group elements. I probably should have said that at the beginning of class. We really just consider main group elements here. The transition elements, the D block, a little strange here. Notice the low affinity, high affinity, okay? So don't think of the number as on a number line. We're looking for, almost think of the absolute value, okay? Absolute value. So really low number here, really high number here, okay? So it increases to the right and up. Okay, I'm going to stop there. If you have any questions, email me.